Hello, and welcome back to another video on the four main ingredients for severe weather. I have discussed lift and moisture previously, and in this video we'll go over the thermodynamics and instability. The previous videos on this series have laid the foundation for a severe thunderstorm event on a synoptic scale, but the thermodynamic processes in this video, as well as wind shear in the next video, I will cover the mesoscale setup. If you are unaware of the synoptic scale and mesoscale features, please go back and watch my video on lift, where I discuss the differences between these two scales, and I'll put the link in the description below to that video. So what role does instability play in severe weather? Along with moisture, instability serves as the fuel for stronger storms and causes air to accelerate from below and rise freely. If you enjoyed this video, leave a like and subscribe, and we'll get started. So the first thing to discuss in order to understand instability is what we call parcel theory. Parcel theory can be hard to understand at first if you're unfamiliar with it, but I'll cover the main takeaways from it. So first, what is an air parcel? This is a pocket of air that has no definite size or mass, and we generally assume it retains its shape as it rises or sinks in the atmosphere. To simplify it, parcel theory dictates that when an air parcel warms, it becomes less dense than the surrounding environment, like you see here in this graphic, and that comes from weather.gov/jetstream. When an air parcel warms, it becomes less dense than the surrounding environment, like you see in the graphic. But that's not all that you need for air parcels to rise, and they won't rise freely on their own. This means that we need a trigger to begin this process, or lifting mechanism. Those lifting mechanisms are some of the things that I talked about in the first video on lift, and they have an impact on the mesoscale. So again, it's important to watch that video and to understand what's going on the synoptic scale that has an impact on the mesoscale. There are several assumptions made behind this theory, and those aren't always true, but this gives a good introduction to instability and a way to visualize where it comes from. So there are a couple more processes to be familiar with, and those are the adiabatic process and the lapse rates. I do have a diagram to help demonstrate this, and I'll show that here. So the adiabatic process refers to the heat exchange between two different things. In the context of the atmosphere, it is the heat exchange between fluids that we're concerned about. And this is what I have sketched here. So the red circle is our air parcel, and the blue circle here is the environmental air that surrounds the air parcel. So the example here demonstrates what we call latent heat release, and this is the heat release from the air parcel to the environment. And so this heat release results from condensation as it heats the surrounding environment. As long as the parcel continues to remain warmer than the surrounding environment, then it will continue to rise through the atmosphere. And the adiabatic process relates to the next process we're going to discuss, and we call those the lapse rates. The lapse rate is the rate that temperature changes with height. And in the context of severe weather, it is the rate the temperature cools with height that we're concerned about. There are three main lapse rates to be concerned with, and those are the dry adiabat, the moist adiabat, and the environmental lapse rate. The dry and moist adiabats are found on the Skew-T and have a fixed rates. The dry adiabat is about 9.8 degrees Celsius per kilometer, and those are shown here on a Skew-T. They go from the bottom right hand corner of the Skew-T and they go up to the top left. And the moist adiabat, those cool at a rate of 6 degrees Celsius per kilometer. And so the reason why the moist adiabat cools at a slower rate is because the moist adiabat is a result from condensation. And so we know from the adiabatic process that condensation is a warming process and it warms the surrounding air. So that's going to slow down the cooling process, which is why the moist adiabat will cool at a slower rate than the dry adiabat. And when we talk about a severe weather environment, it's the environmental lapse rate that we look at. And it is always ranges in between the dry adiabat and the moist adiabatic lapse rate. In general, the steeper the lapse rate, meaning the faster rate that it cools, the more unstable the environment will be. So that was a lot of information, so let's recap. Parcel theory. So first we talked about parcel theory, and that dictates that when you warm a parcel of air and it becomes warmer than the environment, then that air parcel will begin to rise. That assumes, of course, that you have a lifting mechanism to trigger. trigger it. Then we talked about latent heat release from condensation, and so that releases heat from the air parcel to the surrounding environment. And then we talked about the adiabatic lapse, the dry adiabatic lapse rate, and the moist adiabatic lapse rate, as well as the environmental lapse rate as it relates to severe weather. And so that wraps up the discussion on atmospheric stability. And next, I'm going to talk more about the air parcel and some key points for thunderstorms. Before I talk about some of those levels, I want to recall from last video, I briefly covered mixing ratio. And this is looking at how much water vapor is in our air parcel, basically. So I'll demonstrate that again for what that looks like. So we have an air parcel of dry air. And so we're looking at how much water vapor is in that parcel, essentially. And that's what we call the mixing ratio. And this is measured in grams per kilogram. So we're going to show you what this looks like on the Skew-T. So these are the mixing ratio lines that go from the bottom left up to the top right. And the higher your mixing ratio is, the more water vapor you're going to have in the atmosphere, basically. And so we can figure out what the mixing ratio is by looking at how high the dew point is. So the higher your dew point temperature is, the more water vapor you're going to have in the atmosphere, basically. And so this helps us figure out the path that the parcel was going to take. So I'm going to show a demonstration of what I'm talking about here. And so the first point that I want to talk about here is the lifted condensation level. And so that is defined by the height at which an air parcel becomes saturated when lifted dry adiabatically. So what that means is you're going to take your surface temperature and you're going to lift that air dry adiabatically. So it's going to parallel the nearest dry adiabat. And it's going to come up to the point at which your mixing ratio is at. And you find that by looking at your surface dew point, and you're paralleling that to your nearest mixing ratio line. Where these two lines meet together, this is the point at which the lifted condensation level is. And that is where your cloud base is going to be. So that's the height of your clouds, essentially. Once condensation occurs, the parcel is going to parallel the moist adiabats, because now the water vapor in the air has now condensed. So it is now fully saturated and relative humidity equals 100%. So the parcel is now going to parallel the moist adiabats, the lines that are going from the bottom up to the top. Once the parcel becomes warmer than the surrounding environment, that is your red temperature line here, that is where it reaches the level of free convection. So the level of free convection is a level at which an air parcel of saturated air becomes warmer than the surrounding air and begins to rise freely. And so this is where the instability will come from. And then next, we're going to cover a couple more features on the Skew-T here, and then we'll talk about the parameters we use to diagnose instability. And the next feature that I want to recall from last video on moisture, where I discussed the source regions for moisture and for the air masses. So I'm going to bring up the graphic that I showed in the last video. And so we're going to talk about the continental tropical air mass. And that is a layer of hot, dry air that results from surface heating in the desert Southwest. And so this hot, dry air here that originates over here in this region that I've circled, this is picked up from an upper level trough. And then that layer of hot, dry air is transported eastward over your warm sector. And so this hot, dry air in the morning of a severe weather event keeps the warm sector uncontaminated, meaning there's little shower and thunderstorm activity, and allows instability to build during the day. I'll show what I mean on the soundings from March 31st in our case study from this year. And what I want to focus on is this layer in between 850 millibars and 700 millibars. You see a temperature inversion here, meaning the environmental temperature is warming with height, and the dew point in this layer really dries up. You see the dew point line here that goes to the left, so your dew point is decreasing with height. and it really dries up in this layer. That is known as the elevated mix layer, or for short, EML. This is a layer of hot, dry air that is elevated off the surface and then originates from the desert southwest here. This is the continental tropical air mass, and that is transported by the upper level winds to our target region, which in this case is Springfield, Missouri. And this is the morning sounding from this event. So note the parcel path. So this is the dotted line here. You see here. I'll illustrate that for you. And so this, I want to, so focusing again on this region between 700 and 850 millibars, where the environmental temperature is warmer than the parcel temperature. And so this is described as convective inhibition, or SIN for short. So this inhibits strong storms from developing in the morning. In order to erode this, we have to lift and cool this layer of convective inhibition, and that's exactly what happens from the morning sounding. This is from 7 a.m., and then this is 1 p.m., and that's exactly what happened here. So this, you see the shallow layer of warm, dry air that's just above 700 millibars, and so we have completely eroded the convective inhibition from the morning as we have lifted and cooled that layer, that temperature inversion. And so now the air parcel is essentially warmer than the environmental temperature throughout the entire column. And there are two main parameters that we look at when we're looking to diagnose instability, and those are going to be the lifted index, and CAPE. So first, let's tackle the lifted index. So the lifted index is taken at 500 millibars, and it is the difference between the environmental temperature and the temperature of our air parcel. So it is environmental minus parcel, basically. And so this is, in a severe weather setup, this is going to give you a negative value, which indicates an unstable atmosphere. So this means that the parcel temperature is warmer than the environment. The other parameter that is frequently used, and you'll commonly hear it on this channel, is called CAPE. CAPE stands for Convective Available Potential Energy, and this is the energy that is measured in joules, and it is the energy that an air parcel will accumulate from the level of free convection all the way to the equilibrium level, where the parcel temperature is warmer than the surrounding environment. So let's go over the distribution of CAPE. So the distribution of CAPE can impact the kind of severe weather hazards that we'll see. So for tornadoes, we want to see strong low-level instability. And so we can see that by looking at our 3-kilometer CAPE. You see that here. And so this number tells us how much CAPE is accumulated in the lowest 3 kilometers of the atmosphere. So typically we want to see a number that's typically over 50 or 75 joules. And so certainly anything greater than 75 would be considered strong instability in the low levels. And in this case, in Springfield, we have 130 joules of 3-kilometer CAPE, which is pretty strong low-level instability. And so that is, so not considering our wind shear, completely ignoring that, that would be a number that would be favorable for tornadoes. And so now I'm going to go, and then for let's say if we don't have a lot of instability in the lower levels, but we have strong instability in the mid to upper levels of the atmosphere. So let's say that all of our CAPE is here, and we don't have a lot of CAPE down here. That would be an environment favorable for large hail, and not necessarily for tornadoes, because for tornadoes you need the instability be down here below. And so last thing I'm going to cover for instability is going to be kind of the guideline we use for how much to describe how much instability we have. And so that is going to be, we're going to look at the chart for CAPE. And so these are the values that we use and kind of the modifiers that we use to describe how unstable the environment is. So anything, generally speaking, anything that is less than 1,000 joules is considered weak or marginal instability. And so really for CAPE, you want this to be greater than, generally speaking, you want this greater than 1,000 joules per kilogram, but definitely anything higher than 2,500 joules per kilogram would be considered strong instability for the total amount of CAPE accumulated. And so that's going to cover it from this video. Thanks for watching, and I will see you in the next video.